I'm one of the maintainers of Marvell netdev drivers along with my team at Marvell. And personally, I wrote Kimu Smart Fusion to SOC port and upstreamed it. Okay, today I'm going to talk why Printk should be your last resort. I have very less time, so I'll try to talk very fast. So, generally, when I'm debugging something, right, I just look at code, and if I find something suspicious, I just add some print case and then recompile and load the new image. But this is not working at while debugging at customer remote setups, because at customer end it's not that easy to compile the image and try with new image, because they have complex build environments. They'll be using various distros. Mine is like open source, like I just do make and I copy that image to the board and test. And even we work on different time zones, so it delays the root cause. That's when I explored what are all the ways where I can get as much as information from the running system itself. So that's when I came across these tracing techniques. So I'll talk about each technique for a brief, okay? Ftrace is where all the tracing started in kernel, and it's a tracing framework itself, and the trace data will be written into ring buffer internally. When you are new to kernel or new to subsystem, it's very useful to understand the code flow or flow of functions happening inside the kernel. Okay. So historically, if you mount a debug FS, then you'll see the Ftrace exposes the tracefs file system, and if you mount debug FS, you will see the tracefs file system also under debug directory. These are the files we are going to talk about. And one more thing is there are a bunch of traces actually available apart from this function graph, but I have chosen only function graph so that it is easier to understand the code flow, what's happening inside the kernel. And the trace data can be read using reading the cat trace file. And if you do a cat trace of running kernel, right, then your data will always be full, because kernel might be doing something, right, always. It's like scheduler always, scheduler kicking in and timers running. So you won't infer anything from it because your trace is always full. So that's why we have filters. Say this OTX2 is Marvell Octane TX2 driver. So I want to check what all what all things happening with respect to my driver. So I just give a wildcard filter saying echo OTX2 star to set graph function, and clear the existing trace. And max graph depth is the levels of functions you want to trace. Let's say here 3 means function A calling function B and function B calling function C. That's all. So when I send a packet and do a cat trace, if you see here, OTX2 XMIT got called and it is calling append skb, and it is submitting the transmit descriptor to hardware, and transmit complete interrupt has occurred, in turn which called CQ interrupt handler, and it is scheduling the NAPI, and NAPI handler, we are giving back the transmit skb back to stack. See, I'm able to understand the TX flow in one shot. I mean, just imagine you browsing the code a lot compared to this. And with recent kernels, you can even trace the function arguments in the return codes of the functions by default. So if you enable this, one of these options in the tracefs, you can see these two. Okay, trace points. Trace points are static. I mean, developer itself will put some debug points inside the driver, inside the source code. And almost every subsystem has a trace points in it. It has very low overhead, and you can use it in the production also. In the runtime, you can enable or disable any trace point. There are hundreds or thousands of trace points in the kernel. Okay, it's just an example. You need not understand much about this. I just want to bring up that sometimes trace points are necessary for big drivers also, like Mellanox or Marvell or Intel, because if you see our Marvell Octane TX2 running system, we have 3 PCI devices: AF, which is administrative function, which does all the hardware resource management and allocation, and PF is standard PCI SRI physical function. VF is standard PCI SRI compatible virtual function. Here VF cannot directly talk to AF, so PF is a mediator, and if VF wants a request something to AF, it has to go through PF. Almost 6 stages are involved here just for one message. So like this, if anything goes wrong in any one of these stages or in any one of these messages, right? Just imagine I have to throw the print case in all over these drivers to customer and ask him to reload, right? Instead, that's when I introduced Tracepoints to all these drivers. So, and actually I consolidated all the code related to mailbox to some common code and put traces there. Now, if anything goes wrong, I simply enable the trace and I understand what's going inside. This example of Tracepoint OTX2 message alloc is when allocating a message. All the trace points will show up under events directory in TraceFS. RVU is our subsystem name, hardware subsystem name. Out of those, enable is a simple writing to one, enable the trace point, 0 is 0 disables it. Filter I'll talk about later, trigger I'll talk about later. And this is the format. The first four fields you see comes from the tracing infrastructure itself, and the next four are put by me. I mean, developer as per his will. I mean, whatever he feels like useful for debugging, he'll put those fields. And the print format you're seeing down is the format you see in the trace data. Okay, this is an example. Here a message is being allocated by the device PCI standard domain BDF 002:300 and messages of type NPLF which is related to our hardware and size is 40. And it is sent and the interrupt has been raised to the next other device AF. Yeah, you can put trace points and interrupt handlers also because they are very low overhead and message AF send the response back to PF and so on. Okay, let's see a debug example. So one of our customers reported that bringing up an interface is taking longer time. So I asked him to collect the trace, I mean enable the trace, reproduce the issue and get me back with the trace. So this is what I'm seeing. If you see the highlighted one, it is saying that one of the message got timed out. There is a trace point in the error paths also. So it is saying that message got timed out. So PF sent a message and it almost waited 3 seconds and it bailed out after timeout. So that's why he's seeing the delay. But why do we get this timeout? Another observation is this is the CPU number. All trace points are being hit by only single CPU. That means customer is using only uniprocessor configuration. So, and why this message is special? If you see, rest of the messages went fine, but only this message got timed out. If you look closely, it is saying that B bit is set. That means bottom ups are disabled when this message got allocated and sent to other device. Since it's a uniprocessor system, actually the code which kicks the K worker to run the K worker, worker thread, right? That runs in bottom up and it is not getting a chance. So the general code flow is AF gets an interrupt and it schedules a work to process that message and that is not getting scheduled. To confirm this, fortunately we have trace points in work queues also, so I enabled those. Here you see message got allocated, AF got an interrupt and it queued the work queue trace point was hit. It queued the work. After some time message got timed out and when after returning to stack and message got timed out and once bottom ups are enabled again, then the worker is getting a chance to run. So if you see then this message, right, is being called from a NDO op called set RX mode where stack will disable the bottom up and call the driver op. I'm not going to talk about fix for this. I'll just showing the example. Okay, Fprobes. Sorry, for lack of time, I'm not going to talk about Kprobes. Fprobes are a very new approach and lightweight. These are dynamic in nature in the sense you can add the fprobe or delete fprobe in runtime. Trace points has to be present in the code, right, to enable or not. But fprobes are, if you feel like if you want to check whether a function is being called or not, you can simply add an fprobe and enable it. Okay, let's see a debug example with Fprobe. In Octane TX2 Silicon, we support 1 million transmit descriptors. So one of our customers enabled, configured 1 million transmit descriptors and brought up the interface. Then he's seeing a one-on message from kernel, which is at page alloc .c4935. Assume I don't know anything about memory management and all. Not assume, actually I don't know. See, at line number 4935, there is a warning and it is being hit, right? And it's saying order is greater than max page order. So max page order is a constant macro, which is 13, I believe, and order I don't know. Ideally, I would put a print statement inside this if, and I ask the customer to build it and come the next day, right? So that is not needed now. I simply create one probe name. This is the syntax of creating a probe. Order probe is the name of the probe, and alloc frozen pages is a function name, and order is a variable name. And we write to that to dynamic events. It creates a fprobe. And similar to Tracepoints, fprobes will be under events directory. And I enable that fprobe. And as soon as I enable and read the trace data, right, I see a lot of invocations of this function because it's a pretty common function. I mean, it's a page allocator function in the kernel. So it's being called from a lot of places in the kernel, and with almost order is zero order pages. So for this, we have filter. I mean, if your too much data is also not good, right, to debug. So for this, we have a filter. So as a wild guess, since I know max order is almost 13 or 12, I believe, given if order is greater than 7, then only you capture the trace. Okay, I write to this condition statement, I write to filter file, and I enable it and trigger the issue again. And when I do the trace, it is showing that order equal to 17. That's why we are seeing that one on. Okay, now I want to confirm that really my driver is responsible for calling this higher order page 17. Okay, for that we have trigger. So here I'm saying you give me stack trace, I mean stack back trace if order is greater than 7. Okay, and I clear the trace, trigger the issue, and when I read the trace, I see order equal to 17, and indeed OTX to open is cause for it, is calling it. Okay. Okay. Then debugging further, I checked DMA alloc attributes also has tracepoints in it. So what this slide says is DMA alloc attributes is being called with the request of size some 268M, and that is internally it is calling a page allocator a page of order 17. Okay, and this is not happening on my local board. I always debug with a board with my side, and I debug with a customer remote debug session. So when I try the same steps immediately on my board, I see order as 13 for the same 268M size giving to DMA. That's when I looked at the code and I see that this get order, alloc size is same on both boards, but get order is returning two different values, 17 on non-working board and 13 on working board. Just looking at the documentation of that function, it says that it is dependent on the page size. Okay. Then I read the page size on my system, which is 64 KB, and on the customer setup, it is 4 KB. So that's why he's seeing that one on. Actually, we for the Marvell release, we give only 64 KB sizes. So customer agreed to use that 64 KB page. Okay, Kprobes, I'm going to skip. If time is there, I'll cover. Okay. Okay. How many of you know eBPF here? Okay, good. Till now, you're able to observe or capture what's happening inside the kernel, right? Let's say I want to execute some custom logic whenever a event is hit, like probe is hit or tracepoint is hit. Then we can use eBPF. eBPF is a technology that runs sandbox programs in kernel without modifying kernel or not loading modules. I mean, it runs in the kernel space, but it is not a loadable module. eBPF runs in kernel space, but compiled into bytecode. That bytecode is sent to kernel, and that bytecode will be verified by eBPF verifier in the kernel, then just in time compiles to the machine code of the underlying processor. Okay, and after the verification is done, generally this eBPF program, when we write eBPF program, we specify where it has to be attached to. I mean, to a particular trace point, or when a packet is received, or when a fprobe is hit. There is a data structure called maps, which are key value stores used to share data between eBPF programs and user space programs. This picture which shows whatever I described now. Okay, let's as an exercise or example, let's see how we can develop a memory leak detector using eBPF. Okay. The idea is to be hook simple eBPF programs to kmalloc and kfree tracepoints. So here I define two commands called alloc command and free command. Alloc is it does all the allocations like kmalloc, and free does the freeing of the allocations, kfree. So the examples are like inserting a module and deleting a module, bringing up an interface or bringing down an interface. See, as a part of unit testing, see, these big drivers, right? It's really difficult to even review whether we are freeing all the memory allocated by the driver or not. So now we need not dive into any memory management internals, and we can do this simply with eBPF. Okay, here when a kmalloc tracepoint is hit, this tracepoint has an argument of return address like what is the address of the allocated memory. Um, that I take it as key, and the corresponding call trace I take it as value, and I store in a map called map underscore kmalloc. So after some time, our map will look like this. And when kfree is called with ptr1 or address1, say, then I remove that element from the map. Now, whatever left over in this map, right, are the memory leaks. Easy, right? Okay. Though eBPF runs in user space, you cannot, sorry, kernel space, you cannot access kernel functions at all because of security and all, and you have to access only eBPF helpers. To get the call trace of the To get the call trace, we have to use this BPF get stack ID helper, and it expects a map of type. There are different kinds of maps. We'll look at one by one as we go through. Map of type stack trace, and it returns a unique stack ID U32 identifier for the call trace. So now our program changed, like our idea changed, like the map underscore kmalloc will have keys as addresses and value stack IDs, unique stack IDs. If you take that stack ID and look up in the map underscore kmalloc as key, then I'll get the call trace. Call trace is nothing but a chain of functions or list of function addresses which led to the kmalloc. Okay. So this entire program, the struct layout you are seeing, right, kmalloc underscore tp and kfree underscore tp, this we can get from the format file of the trace point, which we have seen earlier. So on kmalloc is a function or eBPF program which gets attached to kmalloc trace point, and on underscore kfree is a eBPF program which gets attached to kfree trace point. Now, simply, as I said, just two-line code on kmalloc. I'm getting the stack ID, U32 unique stack ID value, and I'm storing that as value, and the address of the allocated memory block will be in the one of the arguments of trace point. If you see the above, right, pointer is there, bytes request is there, that I'm storing as key. Okay, let's say, and on kfree it's simple. I just look up the map underscore kmalloc with key as address. If I find that element, I remove that pair altogether. That's all. But there's a problem which I didn't know till that time. If I'm bringing down the interface, it's calling DMA unmap page, and IOMMU DMA unmap page is internally calling kmalloc, which means my assumption is wrong, my idea is wrong, right? So how do I deal with this? I added one more map, which is of kind type array, and a single entry array. Key is always 0. Value is a U64-bit flags, out of which only 1 bit I'm using as a flag. And what I do with this map is, so user space program looks like this, like it sets this flag, calls the alloc command, clears the flag, and calls free command. And kernel space, I first check this map config, and if flag is set, then only I track allocations, otherwise I simply return 0. So let's say if free command like bringing down interface is a cause of kmalloc, it won't be tracked at all, because that flag is not set. Because this is an improvement. Most of the times we see that this kmalloc or memory allocations happen in a loops, for loops, right? Let's say I'm allocating some 10 memory blocks in a for loop. Then call trace for these 10 is same, but in the output it is showing same call trace 10 times, which I didn't like. So I added another map to count the call traces. Okay, that map is also of type hash, and map name is smap underscore count. So value is a counter. How many how many times the same call trace has been called. Let's see the program change. After getting the stack ID, I'm just looking with that stack ID as key, and if element is found, value is found, I increment that. If it is not found, I'm initializing with value 1. So counter is set to 1. Okay, this is a user space. This is um, user space improvement. Like if you see, there is a window between system alloc command and system free command. And there are a lot of memory allocations happening inside the kernel in this window. Those are also getting added to my map, which are showing in my output, which I didn't like. So I improved this user space program uh, to search for only function names with my driver only. So how do I get function names of my driver? Then it occurred to me that all these C code browsing tools, right, we use cscope and ctext, might already be knowing that because they are showing us what is the function name, callers of that function, global variables and all. I just Googled it and I'm giving the entire function names in a file. Now let's see. I have intentionally leaked some memory in netdev sim driver. This is a virtual. I mean, there is no I/O for this driver, and it open looks very simple. So just for you guys to understand, I have I have done these changes in this driver. So I'm allocating num rxq is 10 here. So 10 times I'm allocating memory and 1 byte again. So this is my program. Memleak is a user space executable. Memleak.bpf.o is the bytecode, compiled bytecode. Test.txt contains all the function names of my driver, of the netdev sim driver. So it actually it got that 10 memory blocks were leaked and one memory block was leaked. Okay, till now I talked only about Tracepoints and I stick to only normal raw level files, right? Like I'm just doing echo and cat. But if you are fortunate and you are using a distro like Ubuntu or Red Hat, you can use bpftrace, which is high-level tracing language. It uses LLVM as backend to compile scripts to eBPF bytecode. This language is inspired by C and AWK. So let's say this is an Ubuntu system. I want to find out the number of tagged, VLAN tagged packets going out of all the interfaces from the system. I can simply write one-liner. If you see, the logic in the braces, the BPF program has to be attached to this trace point and the netdev start xmit. And the filter is VLAN tagged. If you see the arguments of this netdev start xmit, right, VLAN tagged is also a flag. You can see the format file of this trace point. So if VLAN tagged is set, then this logic has to be run. The logic is at VLAN packets is a map name, and we are keying with arguments name, interface name, netdev interface name. Count is a built-in function in the BPF trace. So when I run this command and send some tagged packets out of the interface, then I see this, if you see in the down at VLAN packets, 3 VLAN packets sent out of the interface name ENP18S0F1. Okay, so the C code eBPF, I have taken bits and pieces from the samples code in the kernel source. And if you want to know about tracing and BPF trace, you can check out Brendan Gregg blogs and videos. The tool, whatever I have written, I have put it in GitHub. Okay, any questions? So.
Hey, nice talk, by the way. So regarding this eBPF program for kernel leak detection, right, memory leak detection, so we already have this KMM leak, right?
Yes.
So how different and how good is it basically, the approach that you suggested?
No, the point is I want to show, see, if you imagine you writing a KMM leak detector, you want to understand everything, right, about memory and the development time for it. You got it, right? I was able to write this in just 4 or 5 days. The same result you can achieve using eBPF, that's what I want to highlight.
Okay. 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 Good.
It's like we are out of that memory management block. We are able to hook into those trace points, and we were able to cook up something immediately.
Yeah. Hi, Sandeep. So the tracing tools are really good for a program that can sequentially execute. Let's say I'm in an interrupt context.
Okay.
My issue is reproducible only with some timing sequence. And introducing trace point will alter my timing. So the issue may reproduce, may not reproduce. So what tool you recommend in such scenarios?
You're saying this trace point will also add latency?
Yes.
Actually, okay. Why I want to bring up that we have to avoid Printk is because while printing to I/O, right, it will take some delay. But this tracing internally, it will write to a memory only. Whenever we required, we are reading from a file ktrace that data from the memory. Yeah, to answer your questions, compared to other techniques, it has very low overhead. If you're still seeing latency with trace point, I mean, if your issue is that much corner case, then I cannot help you. But I never got that kind of. Yeah. Okay. Okay. Any questions?
Hey, thanks. This was a really nice use case or a unique use case that I have seen somebody using eBPF, right? Just wanted to see, like, if I extend this to, you use this to detect memory leaks in a specific driver, right?
Yeah.
Can we extend it to a specific subsystem? Or maybe, specifically something inside, specifically ARC, and then we have another subsystem under the architecture, right? What will be the challenges if somebody wants to extend this to not for the driver into subsystem?
First, you need to identify this allocation sequence and free sequence. Basically, I'm trying to find if free sequence has freed everything or not, right? Because we got a issue almost 7 or 8 years back. One of our customers reporting that he has run overnight toggling the interface and he is seeing some memory leak. I mean, free -m command. That time I was new to Marvell and almost I checked that code for a couple of weeks, but I didn't find any leak. I mean, everything looked fine. That's when it occurred to me that let's have something like this. And the issue was our hardware takes 2 buffers and keep it itself until we reset the hardware. You got it, right? So there might be corner cases for drivers. Subsystem also, if you identify that alloc and free command, then we can extend to subsystems also.
And any other mapping that you try instead of, the callback? Instead of callback, any other mapping that you try to have the similar results, but you may not fit for this?
Sorry, I didn't get your question.
See, you had a mapping, right, where you see whenever there is allocation, you keep a backtrace mapping, and then when somebody deallocates, you again remove that from your mapping, right? Have you tried any other mapping instead of tracing? Any other way to keep track of those memory allocation and deallocation?
No.
Okay. Thanks.
Even I explored KMM leak that time, but I felt that it is sweeping periodically, checking all the memory objects. Like, so it occurred to me that it is not serving my purpose, or so.
Okay. Thanks.
See, the idea is I want to learn this, so.
Hey, hi. How trace points are managed with hardware interrupts?
How trace points are managed with?
Hardware interrupts.
I didn't get that.
Trace points, you can set it with software interrupts or queues, software queues.
No, if you see, I have used in hardware also. I mean, this is hard hierarchy. If you see, OTX2 message interrupt. There H is set. If you see, that is a hardware IRQ handler. That trace point is in hardware IRQ handler.
Can we put timing logic for that?
Timing logic means?
For a certain time, I want to trace that hardware interrupt.
Yeah, actually for checking the latencies of hardware interrupts and all, we have other tracer also, IRQ soft tracer.
We have to combine it with this?
No, you need to simply choose hierarchies of tracer to current tracer.
Okay,
Yeah.
got it. Thank you.
By the way, I forgot you have to use knob tracer to see this trace points data.
Anyone else? Any questions?
So if I had time, just 1 or 2 minutes, I'll cover up Kprobes also. That is interesting. It's like almost working with GDB. This Kprobes internally uses a like breakpoint so that you can break into almost any instruction, not the function entry or exit. And actually, it's dependent on the architecture specific KBI. So we can use perf to handle that while giving arguments to tracefs files, right? For this kprobe, we have to give what register the parameter will be there and all. So that's why we can use perf to simplify it. Simply do a perf probe add and I say this. I added kprobe to set ring param kernel function. And if you see kernel ring is the structure input parameter for that function and it is dereferencing. I can dereference and check the member values also. So for this you need a VM Linux and I triggered that. I given command which will invoke that function. And if I see the trace file here, I'm seeing that Rx buff length is 0x1000. And not only function, we can also add a kprobe in middle of function also, not a function entry. For this, we need kernel source. So there's the command probe -l. It will list like a GDB where you can add probes. Okay. Here it is showing 32 line number I can add, 38 I can add. And if I want to check some variable, I can give a -v command and it shows what variables can be probed. Let's see an example. I want to check this variable rx underscore local variable rx underscore count. Okay, and this is the syntax. Now, if you see between line numbers 32, there is a comment written. Permitted lengths are 16, 64, 256, 1K. So I want to, and the below logic is doing that. It is rounding up to 1K. I want to check whether that logic is working or not. So I have added the trace point at 38 and 48. If you see at line number 38, Rx count variable is 0x200 because I have given Rx as 512. At line number 48, it changed it to 0x400, 1K. Got it, right? You can check the how state is also changing using Kprobes. But you need perf and you need a source code, VM Linux. Yeah, that's all I have. Thank you. Actually, I had in my plan return probes and all, but due to time constraint, last moment I cut down a lot of slides. Sorry.